Hello and welcome to this lecture. We're going to continue looking at our study of eigenvalues and eigenvectors. So far now, for small cases, we've seen how eigenvalues can be computed, at least a method for computing that. But we want to dig a little bit deeper to understand how the roots and all that look. So we need to know a little bit about polynomials and roots. And also we have not closed the loop, as in we haven't discussed about how to find eigenvectors, right? So we found eigenvalues, how to find eigenvectors, but that we know already. It's just finding vectors in the null space. So I want to comment on that a little bit more in this lecture. Okay. So first of all, polynomials and roots. I've been talking about this fundamental theorem of algebra. A polynomial of degree n with complex coefficients has n complex roots counting multiplicities. Now this counting multiplicities is a bit important. What does that mean? First of all, what this means is number of distinct eigenvalues of an n by n matrix is less than or equal to n. Okay. When you count multiplicities, you have n roots. But if you want to distinct roots, maybe it's less than or equal to n also is possible. Okay, so here is an example. Okay, so here's an example. So here you have a degree 3 polynomial. Okay, and there are some complex coefficients. It turns out it factors as x minus 1 into x plus I into x plus 2i. Okay, so there are three roots here: 1, minus I, and minus 2i. Very easily, right? If we equate it to 0, each of these could be 0, and that's the roots. And the multiplicity is 1 each. Okay, but you can also have other types of polynomials. So here is a polynomial. It's a real coefficient polynomial, but then it factors as x minus 1 whole squared times x plus I into x minus I. Now x minus 1 whole square is x minus 1 times x minus 1. So the roots are actually 1, 1, I, minus I. Okay, do you see that? So this 1 appears twice. Okay, so multiplicity of 1 is 2, multiplicity of I and minus I is 1. Okay, with multiplicity, the roots are 4. Okay, the root for n degree n polynomial with multiplicity, roots are n. So this is how you count multiplicity. When you have powers appearing, you count it that many times. Okay. Okay, so now what happens if a polynomial has real coefficients? Now real coefficients imposes this additional structure on the roots. If a polynomial has real coefficients, if you have a complex root with a plus bi as a root and b is not 0, right, then its conjugate will also be a root. So the conjugate will be a minus bi. So if b is non-zero, you get another root which is different from a plus ba, but it's the conjugate of a plus ba, which is a minus ba. So this is also a root. It's easy to show because the coefficients are real. If you write this equation down equal to 0 and then conjugate both sides, you will get the conjugate will also be a root. Okay. So what this means is if you have degree 1 polynomial with real coefficients, it has one real root. It's very easy. There's nothing much that can happen. If you have degree 2, you may have one real root with multiplicity 2. You can have two real roots with multiplicity 1 each, or you can have two complex roots with multiplicity 1 each. Okay, when you have two complex roots, you cannot have multiplicity 2 because 1 and the conjugate will be, the two different roots and they'll be different. Okay, 1 each. This is the possibilities for degree 2 real coefficient polynomial. If you have degree 3 real coefficient polynomial, you may have one real root multiplicity 3, two real roots, one with multiplicity 1, the other with multiplicity 2. That is also possible. Or you can have one real root and two complex roots, multiplicity 1 each. Okay. So you see in all three cases, when you have a degree 3 polynomial with the real coefficients, you have one real root at least. Okay. One real root is there. What happens to the remaining? Multiple possibilities are there. So you have similar structure for any n. Okay. So if you n4, you'll have a whole bunch of possibilities. So when you have real coefficients, there is this additional structure because of the conjugate also being a root. Okay, anyway, now let's move on to finding eigenvectors. Okay, so multiplicity of roots is one factor. So this will play some sort of a role in our ability to find eigenvectors. You'll see how it works. Okay, so if you have lambda being an eigenvalue of t, then t minus lambda is singular. I know that. So every non-zero vector in null t minus lambda is an eigenvector with eigenvalue lambda. Okay, so null t minus lambda is in fact called the eigenspace of lambda. Okay, because the space, because it's a subspace and it has many vectors. And every non-zero vector is a eigenvector, so we call it as eigenspace. Okay. The interesting question now is, see, anytime we have eigenvectors, all linear combinations of those vectors also sort of not increasing dimension, right? So what is interesting is how many linearly independent eigenvectors are there? That question is answered dimension of null t minus lambda I, right? So that many linearly independent eigenvectors you will have with eigenvalue lambda. Of course, not mentioned that here with eigenvalue lambda. Its dimension null t minus lambda I. Okay, why? Because this has to be greater than or equal to 1, right? It cannot be 0 because t minus lambda I is singular, no, if lambda is an eigenvalue. And how many linearly dependent eigenvectors are there with eigenvalue lambda? It's dimension of null of t minus lambda I, and this is greater than or equal to 1. It cannot be 0, okay, because t minus lambda I is singular, okay. So, it's a question of just finding the null space of this guy, okay. So, what is the set of linearly independent eigenvectors? The basis for the null space. So, given any matrix, we know how to find the basis for the null space, and that is all you have to do to find eigenvectors, okay. So, a word on multiplicity. There are two types of multiplicities for an eigenvalue. One is called algebraic multiplicity. We saw it already. Eigenvalues are roots of a minus lambda I, okay. If lambda naught is an eigenvalue, algebraic multiplicity of lambda, denoted algmul, okay, algebraic multiplicity of lambda, is the multiplicity of the root lambda naught in the polynomial determinant a minus lambda. Okay, so if it appears as x minus lambda naught and other terms are different, then it has multiplicity 1. If it appears as x minus lambda naught squared, then it has multiplicity 2, x minus lambda naught cubed, multiplicity 3, so on. Okay. So, sum of all the algebraic multiplicities of all the distinct eigenvalues is equal to n. Okay, so that is something we can see. Now, there is also something called geometric multiplicity. Geometric multiplicity of lambda, which we denote as geomul of lambda, is the dimension of null t minus lambda naught. Basically, it is the number of linearly independent eigenvectors for eigenvalue lambda naught. That is the geometric multiplicity. Okay. So, it turns out this inequality is true. Geometric multiplicity is less than or equal to algebraic multiplicity of lambda, but it is of course greater than or equal to 1. At least 1 is guaranteed, but you may not go all the way up to algebraic multiplicity. It can be less than or equal to algebraic multiplicity of lambda naught. This proof is slightly involved. We will see that later. We will see a lot of examples where this proof is illustrated. We will sort of get an idea of it from there, but the proof itself we will do a little bit later on in subsequent lecture. Okay. So, what this means is, if you add it up, sum of geometric multiplicities is less than or equal to n, okay, because sum of all geometric multiplicities over all distinct lambda naught, right, is less than or equal to sum of all algebraic multiplicities, which is n. So, sum of geometric multiplicities is less than or equal to n. See, these are interesting factors. These definitions are interesting. We will think more on this later on in subsequent lectures. Okay. So, I am going to close with a whole bunch of examples where I have taken all upper triangular examples so that my calculations do not become very painful. Okay. Now, upper triangular, right, when you do a minus lambda I and then find determinant, what will you get? You will just get 1 minus lambda, 2 minus lambda, 5 minus lambda, right. So, values on the diagonal itself are the eigenvalues. Okay, that is the nice thing about upper triangular, no. Even lower triangular, that is true, and diagonal also, that is true. For all these guys, the values on the diagonal are the eigenvalues themselves. Okay, so you can just prove it by writing a minus lambda I, and then you will see only this will be non-zero, this product will be non-zero, everything else is 0. We saw this example soon enough, right. So, what are the eigenvalues of this 1, 2, 5? It is 1, 2, 5. So, how do you find eigenvectors? Let us try and find eigenvectors. Maybe I will show you how to do this for the first case. I think let us do this. A is 1, 2, 3, 0, 2, 3, 0, 0, 5. So, we know that the eigenvalues are 1, 2, 5. Now, if you look at A minus 1 into I, it will be 0, 2, 3, 0, 2, 3, 0, 0, 5. Okay. You can try and do some pivoting and all that, but it is very clear that you have got a 0, 0, 0 here. So, the eigen vector, right, the null space of this, null of A minus I, okay, it has got dimension 2, dimension 1, right, it has got rank 2, no, this A minus I has rank 2. You can quickly see these things, you should start to see very quickly. So, you have got 2 pivots here, 2 and 5, so this 2 columns here, these 2 are linearly independent. So, dimension of the null has to be 1, right, rank itself is 2, so dimension of the null has to be 1, and the basis vector also is very easy to find. Once you have a 0, 0, 0, and all you have to do is, basis is just 1, 0, 0, okay. So, lambda 1 has eigenvector 1, 0, 0, and that you can quickly see. If you multiply by 1, 0, 0, you get 100, right. So, A times 100 is actually 100, right, 1 into that. So, eigenvalues. So, let us try A minus 2i. So, notice what you get here, minus 1, 2, 3, 0, 0, 3, 0, 0, 4. Interesting, isn't it? So, now you see here, this has also got rank 2, right. Why rank 2 here? So, these two are linearly independent. These two are dependent, right. So, it is very easy to quickly see here, these are dependent, okay, dependent, because this, if you multiply by minus 2, you get this. So, these two are linearly dependent, okay. So, null A minus, so if this is not apparent, you have to do some linear elimination and all that, but in this case, it is very, very easy. So, dimension is 1, and even the solution is easy to check, right. So, how do you find a vector here so that it's 0? So, you have got minus 1 here, 2 here. So, if you put 1 in the first column, you should put, or if you put 1 in the second entry, it is 2, you should put minus, you should put plus 2 here to get that, okay. So, basis is 2 comma 1 comma 0. So, if you multiply by 2 comma 1 comma 0, you get 0 here. So, this belongs to the null space, okay. So, you can quickly check that, 1 2 3 0 2 3 0 0 5 multiplied by 2 1 0 actually becomes what? Actually becomes, you multiply with 2 1 0, you get 4 2 0, which is the same as 2 times 2 1 0. So, you get eigenvalue 2, okay, it checks out, right. So, notice how we find the basis for the null space and it works out. Let us do the last problem, last one. A minus 5i is going to be 1 2 3, I am skipping the thing quickly, A minus 5i, I am sorry, minus 4 minus 3 3 0 0 0. So, here again you can go row wise and see quickly, identify null A minus 5i has got dimension 1, okay. So, here I do not know if you can quickly find out the the thing without solving. You have to pick it as, right. So, let us just solve 0 0, 2 minus 3 0, 3 3 0. So, times v1 v2 v3, or you can write x1 x2 x3 equal to 0 0 0. Identify this as the free variable, okay. So, you set x3 to be 1. If you set x3 to be 1, everything else will be determined. If x3 is 1, x2 has to be also 1, okay. And if x1, x3 and x2 are 1, just back substitution, right. In the second equation, you see that x2 has to be 1. In the first equation, you see 5, x1 has to be 5 by 4, okay. So, the basis for this guy is 5 by 4, hopefully that is okay, 1 1, okay. So, you can quickly check that 1 2 3 0 2 3 0 0 5 multiplied by 5 by 4 1 1 is actually what? 5 by 4 plus 5, that is 25 by 4, 5 5. So, it is 5 times 5 by 4 1 1, and that also checks out, okay. So, notice how you get the answer quite easily, okay. So, I am not going to show you every other example. I will just talk about the multiplicities here. So, here it is 1 1 1 1 with multiplicity 3, right. So, maybe I should do this example, or maybe I will pick some example from here, okay. Maybe one example from here and one example. I mean, I will urge you to work each of these things. You will get interesting little answers. Maybe I will do this example, okay. This example, 8th example, okay, just to get you a sense of how this works, okay. To show you the arithmetic multiplicity, not arithmetic, algebraic multiplicity and geometric multiplicity relationship, I will do this one, okay. 1 1 0 0 3 4 3 5, etc., right. So, let us just write this down. All the examples can be done. They are very, very, very interesting and simple, because and then what did we get as the off diagonal entries? 3, 4, 3, 5, 6. Okay, so this is what it is. So if you do a minus, so first of all, what are the lambdas? Lambdas are 1, 1, 2, 2, right? Just values along the diagonal. These are upper triangular. So 1 has multiplicity algemal, right, of 1 is 2, algemal of 2 is also 2. Got two guys here, 2 guys here. Let's check out geometric multiplicity, right? So if you look at a minus I, I'm going to get 0, 0, 0, 0, 0, 0, 0, 0, and then 3, 4, 3, 5, 2, 6, 0, 2. Okay, so clearly rank is 2, right? So if you look at null a minus I, you get dimension 2. So which means geometric multiplicity of 1 is also 2. Okay, very nice to see. Now what is the basis? You can find a basis. This basis is very easy. 1, 0, 0, 0 will be a basis. 0, 1, 0, 0 will be a basis. These two you can check quickly are eigenvalues, eigenvectors with eigenvalue 1. Okay, let's try 2 now. Oops, sorry, I forgot this here. It should be 1, 1. Okay, a minus I. Apologies. So a minus 2I, if you do, you're going to get minus 1, 0, 3, 4, 0, minus 1, 3, 5, 0, 0, 0, 6, 0, 0, 0, 2. Okay. So the crucial part here is the rank here is 3. Okay. So you have 3 pivots you can find. The rank will be 3. If you want, you can do the exchange and all that and check, but you will get rank is 3, which means null a minus 2I has got dimension 1. So geometric multiplicity of 2 is actually only 1. Okay, so you don't have 2 here, which becomes strictly less than 2, which is algebraic multiplicity of 2, right? So you can find a basis also. This is not too hard. It's a little bit interesting, so maybe I'll just quickly solve it. Okay, so I need to solve this equation, right? So minus 1, 0. So it's only dimension 1. 0, minus 1, 3, 5, 0, 0, 0, 6, 0, 0, 0, 2, and this has to be equal to, I'm sorry, times x1, x2, x3, x4 has to be equal to 0, 0, 0, 0. So this is my equation for null space, right? So now if you look at this, the only way I can have this true, I mean, so you need to have x4 equal to 0. So do you see that? So if you take out the last equation, it says 2 times x4 is 0, 6 times x4 is 0, so you get x4 equal to 0. Okay, you can write this equation out, you will get x4 is 0. So once x4 is 0, this becomes a free variable. I can pick it as anything I want, so maybe I'll set x3 to be 1. Okay, so this is a very usual way of doing it. When you have free variable, you set it as something non-zero, usually 1. Other things is 0, so you get this case to be true. So once x3 is 1, you will see that x2 has to be 3 and x1 has to be 3, right? So you get that the basis is just 3, 3, 1, 0. Is that okay? So that's the basis, and you can multiply and check that, 3, 3, 1, 0. Let's check that. 1, 0, 3, 4, 0, 1, 3, 5, 0, 0, 2, 6, 0, 0, 0, 2 times 3, 3, 1, 0. What am I going to get? 6, right? So that I got 6. I better get 6. So I get 6 here again. Here I get 2, and here I get 0. So that's 2 times this guy. It checks out. Okay. So you can solve this. I'll urge you to solve each and every one of these things. They all give you different cases. I'll tell you very quickly how this will work out. This has got multiplicity 3, algebraic multiplicity 3. Geometric multiplicity will just be 1. Okay, so when you subtract 1 from it, you see that the rank is 1, so rank is 2, so nullity will be only 1. So geometric multiplicity will be 1 for this guy. Here you have 2 and 1, right? Algebraic multiplicity 2 for 1, and then the eigenvalue 2, right? 1, 1, 2. And for 1, algebraic multiplicity is 2, but geometric multiplicity will only be 1. And for 2, algebraic multiplicity and geometric multiplicity will be 1. Okay. So likewise, you can work out every single case very quickly. 1, 2, 3, 4 is very easy, each with algebraic multiplicity 1, each with geometric multiplicity 1, easy. So this case is actually algebraic multiplicity is 2 for 1 and 2, but geometric multiplicity is only 1. So likewise, you can solve each and every one of these cases. Okay, thank you very much.